Welcome to the Computational Medicine Podcast, where we discuss AI and computational tools being deployed in medicine. I'm Alex, a doctor working in London. Today we're talking to Vivek Natarajan from Googlehealth about his work in helping to build MedPalm 1 and 2. Currently, the two best general medical machine learning models are GPT4, built by OpenAI, and MedPalm 2, built by Google, both of which are scoring over 85% on the USMLE and similar medical licensing exams. Vivek told us about his team at Googlehealth and how they built MedPalm 1 and 2, and where he sees models similar to this being deployed in medicine in the near future. Okay, so thanks very much, Vivek, for agreeing to chat to us today. The work that you guys are doing at Googlehealth looks absolutely fantastic. Really loving all the stuff. So could you just kick us off by telling us about your background and how you came to work in on the projects that you do currently?
Sure, Alex, and thank you for inviting me. It's a pleasure to be over here. So as far as my background goes, I like to call myself a product of the MOOC revolution, massive open online courses. So I work in AI today and have been working in AI for the last decade. But when I was doing my undergrad back in India, uh, I knew nothing about machine learning and AI, and I just happened to stumble into it while browsing the internet and came across a couple of courses from Professors Yasser Abu Mustafa at Caltech and then Professor Andrew Ng at Stanford. And yeah, the first few minutes of watching that content, it was very clear to me that this was, going to be incredibly powerful, even though they were like talking about, pretty basic old school machine learning algorithms like SVMs, none of the deep learning or neural network stuff, but it looked really cool. The idea that you could teach machines to learn from data without having to hard code every single constraint or logic into the model was fascinating to me. So I wanted to learn all about machine learning and AI, and so when I went to grad school, I took up as many AI courses as possible, covered all sorts of things from graphical models to neural networks, and then I was really lucky when I graduated that I became one of the first few engineers at Facebook AI Research, which was just spinning off in 2014, and I had this very nice role at the intersection of research and production, where I got the opportunity to take the best models from that Facebook AI Research was building and put them into products at scale to hundreds of millions of users. And so in that process of doing that, I learned all about building deep learning models, right from training to inference and deployment and learning from feedback or whatever feedback was in those days. And for 4 years, I helped do this repeatedly across a bunch of different verticals, ranging from speech recognition to natural language processing to computer vision, and a little bit of robotics towards the end. And pre-transformers, these were all very different models. And so each domain used a different architecture. Like vision was resonant based, NLP was still using RNNs and LSTMs, and speech recognition had a mixture of Gaussian mixture models and then DNNs combined. It was a very complex system. But it was clear, when you were introducing deep learning, you were not only beating research benchmarks, which were set for 20 years, but you were also lifting key metrics on some very important business critical verticals like engagement on newsfeed or revenue on ads. And so this deep learning thing was clearly working. So I said that access to education kind of changed my life. The other recurring theme for me was access to healthcare. So I grew up in parts of India where in the surrounding villages, for people, going to see a doctor would mean giving up on a day's wages, walking, 30, 40 miles in extreme sunshine, hot weather, inclement weather. And for most people, that was not palatable. And so it was quite common that a lot of people would not see a doctor at all in their entire lifetimes. And that meant adverse health outcomes, reductions in life expectancy and everything. So I always wanted to do something about this. And even when I was in my undergrad, the idea that I pitched for my final thesis proposal was called Ask the Doctor Anytime, Anywhere. It was prototyped using basic machine learning technologies, SVMs, and expert systems back in the day. And obviously it did not work very well, but the idea stayed with me. The fact that you could probably put a pocket GP into people who did not necessarily have access to the best doctors in the world, but that pocket GP would be a great substitute, maybe as good as a world-class physician that you have access to in Western countries like what I do right now in California. But as a great man once said, you don't take a straight path to your goals and dreams. It's a more winded one. And so I took down the AI route. But thankfully for me, around 2017, 2018, I was again generally thinking, okay, this deep learning and AI thing is obviously clearly working, and transformers had just come onto the scene. And I wanted to then work on something that could have a lot of impact. And so I was asking this question, where is AI going to have the most impact? And for me, that answer was again healthcare. And so I wanted to go into it. And thankfully, I got this opportunity where Googlehealth was just spinning off with like researchers from DeepMind and Google Brain coming together. And I got the opportunity to come in and lead some important research. And so since then, I have been here trying to build out ever increasingly general medical AI systems that can be deployed safely in clinics around the world. And one of the outputs of that is this MedPalm large language model system. So, yeah.
Fantastic. So could you give us a quick summary? Well, yeah, tell us about MedPalm.
Yeah, sure. So MedPalm is this large language model that we have designed at Google, specifically for applications in the medical domain. The core thesis of MedPalm is even if you have like a very strong general purpose large language model like GPT-3 or whatever, medical domain is like specialized enough that you would want to maybe pay more attention to it, maybe like get more curated data and more curated expert demonstrations to be able to teach the model the adequates of the medical domain. And so that is what we did in MedPalm, where we took a general purpose model and then we aligned it to the requirements of the medical domain. And then we showed that when you evaluate the model using expert clinicians, you find that a lot of the important axes that we care about in medicine, such as factuality, precision, recall of medical knowledge, medical reasoning, potential for harm and bias, all of those things improve quite significantly. So that was MedPalm, the paper that we put out in December. That's the core idea. But if you look at like medical question answering itself, that has been a grand challenge for a long period of time. So there has been like research proposals dating back to the 1980s from researchers at MIT and other esteemed institutions talking about building expert systems for clinical decision support. And people have been iterating on this version on this problem for a long period of time because the impact is very clear. But I would say that maybe until December of last year, there hasn't been specifically a lot of progress in this space, even with all the breakthroughs on transformers and LLMs. And so if you look at like this one specific benchmark that has become particularly popular in the last few years, the USMLE question answering benchmark, the US medical license exam questions, the performance on it kind of hovered around like 40 to 50%, even with like some of the best transformers and LLMs from some of the best AI research labs in the world. But then with our MedPalm work, we showed that these large language models, when you train them on a lot of data, internet scale data, they do pick up medicine and medical knowledge, and they're able to do very well on these standardized tests. And so our model improved from the state of the art by like over 17-18% back in December. And since then we've talked about MedPalm 2, which is now performing at expert test taker level. But then I mean, this is cool. I mean, this is clearly showing progress, but then like you're probably not going to use these models to take USMLE tests or something similar. I think you're going to use it for better applications in the real world. And so that is where we were kind of like trying to get with the MedPalm paper, where we tried to simulate more realistic application scenarios. For example, what users might ask such a large language model. And then we had the model evaluated by experts and by lay users in terms of a bunch of different axes. And so that is where we clearly see value, because we see that these models are fast approaching what clinicians can do today. But I think the more interesting thing is they can actually be really complementary to clinicians. So I'll pause there.
Fantastic. And just brilliant. I don't think that it's kind of crazy that the internet hasn't absolutely exploded in response to this, just because like MedPalm 2 and ChatGPT4 are far and above the best models, the best any sort of AI AI model has come they are both right now in 2023 scoring at expert levels in these exams. It is absolutely sensational. I mean, the implications of this are just so multifarious. It's absolutely fantastic. Really, really great work. I have no idea how. Obviously, I've seen that there's been a lot of there's been a big splash about this in a lot of the media. So The Economist, all the big newspapers have been writing about this. So yeah, it's really, really fantastic stuff. I think I read in the paper that in the MedPalm 1 paper that the difference between the other models that you mentioned that were still hitting at that 40 to the low 60s mark and MedPalm 1 was the scale of the model and the prompts. So could you just tell us a bit more about that?
Yeah, sure. So one of the the core thesis that we have is that as you train large language models with increased parameter counts on large corpuses of medical text, not medical text, like internet text, basically. And internet basically contains everything. I mean, it contains information about medicine, law, physics, chemistry, biology. As you start doing this, even though the objective that you're doing is itself fairly simple, in the sense that what you're doing over here is downloading the entire internet text corpus and making the model predict next words, right? So it's very simple when you state it that way, but it's actually under the hood, hiding a pretty complex multitask objective where, in order to do this task really, really well, the model needs to understand not just like syntax, but also semantics, and also understand nuances about physics, chemistry, mathematics, medicine, law, everything, because it's all encoded in the web. And so in order to like really be able to like do a good job at this next word prediction, you need to be able to do all that. And what we see is, as you do this at more scale, in terms of the number of parameters, you start to observe this phenomenon of emergence. And so what emergence is basically capabilities in models that you don't observe when the number of parameters is small, but you observe when you scale the model to beyond a certain size. So for example, if you say go from 5 billion parameter LLM to like maybe 100 billion parameter LLM, you see that on certain tasks which require reasoning, say in arithmetic, the 5 billion parameter LLM is basically performing like at random, whereas suddenly the 100 billion parameter LLM is now performing at like say expert level and getting like full accuracy. So we're starting to see basically better reasoning skills emerge as we scale up these models to more parameters and in concert scale up the data that these models are trained on. And so that has implications for medical as well, because when you have to answer medical questions, you often have to reason about a bunch of information about the patient, their symptoms. You have to recall medical knowledge, and you have to comprehend like the lab records or whatever in there. There's a lot of reasoning involved over here, right? And so what we are essentially seeing is, as you scale up the model is able to do better at this kind of medical reasoning that is necessary. And so that is what we see. So if you look at some of the scaling plots that we have in the paper, there is a linear increase in performance as you scale up the model parameter, go from like I think an 8 billion model to 62 billion model to 540 billion model. Like there's a linear increase in performance, and I would dare say that in fact the performance seemed to be accelerating on these benchmarks as you scale up. So
fantastic.
Yeah, it comes back down to the fact that we observe this phenomenon of emergence of new skills as you scale up these models.
So you think okay, fine. And so do you think once you get to, sorry, was it that once you were getting to the much higher sizes of the models that the relationship became a bit non-linear due to emergence?
That's right. So they seem to be getting even more better. We don't know how this will behave as we scale up the models further. So I think that's an experiment that I think a lot of people around the world, like in these research labs, are trying to do now, and we'll probably get to the answer very, very soon. But so far from what we have seen in MedPalm, it's that there is now a nonlinear increase. But I would also maybe caution that these benchmarks may not be reflective of real world use cases. I mean, they're just one test in one setting, uh, and maybe they're more appropriate for assessing human potential doctors and not like AI itself, because the kind of intelligence that you have in an AI is, I think, quite different from what you have in humans. And then I think, yeah, then the second part that you asked about, like prompts and the importance of it, I would maybe also point out that it seems that the larger models, uh, it's easier to align them to the requirements of the domain compared to smaller models. So one of the ideas that we presented in the MedPalm paper was prompt tuning. And prompt tuning itself works only when the knowledge that you need the model to answer a given question or reason about a given question is already encoded in the model. But if you have a smaller model with smaller number of parameters, then maybe there's not enough parameters to, encode all the knowledge that you see on the internet. And so in that setting, it may not work. But if you have all the knowledge encoded, then at inference time, when you get a new question, it's more of a question of like pointing the model to the right part of its knowledge base. So you can imagine a neural network as like a giant library. And with prompt tuning, with that specific soft vector instruction that we are teaching the model, what we are doing is in this setting, in this giant library, maybe you should go to that room or to that shelf of books, and that is where the answer is going to be. So you're kind of like directing the model and providing a torchlight to the right direction of like, medical information that is encoded in the model over here. So what we see is that idea of prompt tuning as an alignment technique works much better as you scale up these models, just because the knowledge itself is already encoded. And so it's more of a question of pulling out that right knowledge in the right method or format to use it appropriately given the question in medical context.
And how did you know which prompts were referencing information that the model had a good knowledge base on versus prompts that didn't? Say, what was your metric for measuring the quality of the prompts?
So given that this model is trained on language, we decided to use expert demonstrations. So we wanted to ask a clinician, for example, how, if you were to like teach a language model to answer a given medical question systematically, how would you go about doing that? And so we worked with them to craft the prompts, and we actually saw that human intuition in terms of providing a step-by-step breakdown of the medical reasoning process, what we also call chain of thought in other settings, helped quite a lot. And so those breakdowns we took as few short examples, we engineered that into the prompt, and then we used another bunch of expert curated demonstrations to learn these soft prompt vectors that is done in instruction prompt tuning. So I would say it actually came down to using human intuition and human knowledge and working with expert clinicians to craft this set of demonstrations and instructions to be used to train and align the model.
Fantastic. And what type of model does MedPalm use?
Yes, so under the hood, the MedPalm model is based on the Palm family of large language models from Google, and these are decoder-only large language models based on transformers. So I would say that like the current large language revolution that we are seeing around the world, it's primarily due to breakthroughs in three things. One is the emergence of transformers in 2017. Then the second thing is the emergence of decoder-only large language models, which was first done by GPT-3. And I would say the last one is the emergence of strong alignment techniques, such as RLHF or instruction prompt tuning, that allow you to constrain the behaviors of the model and make it behave well in important applications. So yeah, I maybe don't want to talk too much about transformers. I mean, I think we all know at this point of time, but it's a remarkable thing. It's a differentiable trainable computer, which is brilliantly expressive in the forward pass. So you have this idea of self-attention, which is a generalization of this concept of message passing in traditional machine learning and graphical models, where as you go through the different layers in the network and reach different nodes, each node is allowed to look at the values of its neighbors and then update its own values based on what it sees. So that is a very general and expressive operation, and that may not have been available to the full degree in other architectures that we had such as RNNs or LSTMs, which are more constrained to their immediate neighbors. And same with convolutional neural networks. I think the other thing about transformers is it's also very differentiable and learnable using tools that we have at our disposal for teaching these neural networks, which is gradient descent. The way these transformer blocks are put together with the residual networks allows you to train very deep and large transformer models using gradient descent techniques. And the last thing about these transformer models is the fact that it is remarkably compute efficient with a lot of parallel operations, and it can run very well on our hardware such as GPU and TPU. And so the implication of this is that transformers are remarkably general purpose. They can cobble up any kind of data. I mean, we've shown that it works with text, but we're also in computer vision now using vision transformers. In speech recognition, we are using transformers again. Robotics is now starting to use transformers. So it's now, it's everywhere. And it's been 6 years since the transformer architecture came out, but it has also proven remarkably resilient. And so the zeitgeist is, don't touch the transformer, keep it as it is. Work more on everything around it, which is the data and the compute infrastructure, and scale it. And so that has, I think, been the core to this new large language model revolution. And so there have been various classes of transformer-based LLMs. BERT was one model, which was an encoder-only model. And so when I say an encoder-only model, it can take a sentence and generate a contextual representation of it, but it doesn't generate a response. It doesn't generate an answer. It just generates a representation of your question. So it's useful for certain applications, such as classification or natural language inference, but it's not useful for doing stuff where you require generation, like in medical question answering. But then there have been other classes of models which are also called as encoder-decoder models, where you first take a natural language input or a sequence, generate a representation of it, and then once you have the representation, you seed that into the decoder to produce probabilities over your token sequence. And so that can be used to generate the output. It's a very nice concept, but it's also a little tricky to train. But I think the fun breakthrough again back with the GPT-3 paper was the fact that they showed that decoder-only models, where you took out the encoder part and just had a very simple decoder-only large language model and scaled it up and threw the entire internet corpus at it, that can generate text very, really well. And so that was the big breakthrough. So transformers and decoder-only large language models. And then the third idea, which I mentioned, was around alignment. So the idea of chatbots is not new. And a lot of people may remember that Microsoft had this chatbot known as Tay, which was put out, and then it went rogue and I don't know, within 24 hours of this being put out. But we've now had ChatGPT, GPT4 out in the real world for several months, and we've had very few instances of people reporting models going wild or crazy. It's not that very easy to jailbreak and get sensitive information out from the model or make it behave wildly. And so that is, I think, a breakthrough in alignment in terms of being able to control these models and being able to do that with not a lot of data. So in the MedPalm paper, we showed one very simple alignment technique, which we call instruction from tuning. And we showed that even using 100 examples might be sufficient to constrain the behavior of a model for use in safety critical applications such as medicine. But then I think others have shown reinforcement learning with human feedback. It's more complex, it requires more data, but then it also works really well. It's a general purpose alignment technique. And using that, you can now constrain the behavior of this model and make it perform within guardrails, work within guardrails, answer within guardrails. And I think that is very, very important for applications in the real world. So these three things are pretty much the basis of the large language model revolution, and that is what Palm builds on and MedPalm builds on.
Fantastic, great stuff. And where does Google see MedPalm being implemented in the near future?
So yeah, we still are in, I would say, the research phase. Medicine is a safety critical domain, and yeah, so you want to move responsibly over here. And so we want to work with stakeholders in the medical ecosystem whether that's doctors, whether that's payers and providers, or pretty much everyone, to understand the implications and the best uses of these models. And that requires deliberate and thoughtful actions. And so we don't think we can just put the model out there in the real world and let people use it. So we're working through Google Cloud and allowing a bunch of trusted testers to use this model. And then we will gather feedback from them in terms of how the model is working, and then use that to further improve the model. And so we'll do this deliberately and responsibly, but we also understand the implications of this technology. So we want to move fast over here. So we will do that as safely as possible.
Fantastic, great. And with the I guess the select few people that they're trying it out with right now, it's a little bit kept on the down low. But I'm just wondering what the sort of quality metrics are when you deploy these sort of generative AI. When you deploy these generative AI models, are you able to mention, say, sort of what areas they're roughly thinking of using them in? Because I guess what I've been reading around the, say, generative AI side of things is like you said, because medicine's such a safety critical area, it can be very good for, say, information gathering and refining. So I can think of a good number of or at least a few off the top of my head, medical startups that essentially sell services to the NHS by they're almost like a chatbot. The one example is sort of Ada Health. They kind of, when I was working in GP, I saw one of these sort of pro formas come through. So it's essentially a chatbot. You tell it your symptoms, and then it comes up with a pro forma of, based on what your symptoms are, some sort of pro forma of say the key things that you would ask for whatever the issue that they've come in with is, and it did save a bit of time. I can imagine that is one area that Google is thinking of. The sort of using the fantastic technology that you've built to, but with these fair sort of checks and balances that make sure that it's being deployed but safely. Other than, say, like a kind of pro forma chatbot type thing, are there any other sort of areas that you're able to talk about that you can think they might be thinking about deploying it in?
I can't talk about Google specifically, but I guess GPT4 and other powerful large language models have been out there, and naturally people in and around medicine have been using it for a bunch of different applications. I think there's a spectrum of use cases for these large language models. Some of them maybe are less safety critical, more workflow style tasks, and that maybe depends a little bit on the overall medical system in place as well. But you can imagine, like, doctors in the US, for example, spending a lot of time writing notes or pulling information from different sources. And same with like PCPs and nurse practitioners, a lot of documentation work. And I think a lot of it can be automated away, or it can be made much simpler, so that doctors and also our PCPs and NPs can go back to focusing on what they are meant to do in the first place, which is actually providing care and interfacing with the patient. So I feel like that is where maybe we will end up making the most progress in the near term. As far as like clinical decision support goes, I expect that these models will have a role to play, but it will almost certainly for the next few years be with doctors in the loop. So I don't see a scenario where, for example, these models may be deployed without a human in the loop to correct the answers, or so it's more probably going to be like clinician facing, where these models surface some interesting thoughts and responses around decision support, and then the doctor decides whether to use them or not. But I think the end state of the long-term goal is very clear in terms of using these technologies to create something that can ultimately talk directly to people worldwide and provide them with a world-class GP in their pockets.
Fantastic, exciting times. Very exciting. So how does the team at Google Health work to increase the collaboration between those with medical expertise and those with computational expertise?
Sure. So I think if you look at our team, it's an interdisciplinary team. So we have not just engineers and researchers, but we also have uh, doctors with different kinds of expertise in different areas. And if you want to make a dent in medicine, then I think you need people from both backgrounds, but also you want to have people who are willing to understand the vocabulary of what of the vocabulary that the other party uses over here. And so you want engineers and researchers who are very willing to learn about the intricacies and nuances of medicine and biology. And at the same time, you will want, doctors and clinicians on your team who understand the capabilities of these AI systems. And once these two parties are able to do that, or these groups are able to do that, then I think they assimilate together and become part of a whole, and then they can work together. And so if we look at it, like when we start off new projects, we ask our clinicians in terms of, okay, is this problem something worthwhile solving? Does this address an unmet need in the world today? And then when we, for example, are formulating what data sets that we need, or how to evaluate these models, what metrics to use, again, we work very closely with our doctors and clinicians on the team to formulate that, because their inputs are, I think, more useful than an AI researcher who would probably be thinking about, cross entropy or negative log likelihood or common objective metrics, but not how this model would actually be used in a real world workflow. And so thinking through that and designing the model, accounting for the workflow where it would be deployed, is, I think, critical in terms of ensuring that these models can have an impact in the real world. Because otherwise, what you end up having is maybe a cool model with some interesting things that it can do, but it may not be optimized at all for any sort of use in the real world. And you then have to go back and redo all those things, and that can be painful. And so it's better when you're starting off a project, you think through all of those things. You don't necessarily have to rush, but be more deliberate. And then once you do that, I think your translation in the real world will be much, much quicker. And so that is what we try to optimize for.
Fantastic. And what are some of the best advances or the best efforts that you've seen to increase the quality of medical data sets?
Honestly, there haven't been a lot that I am aware of. I know a few resources out there, such as PhysioNet with MIT. It's affiliated with MIT, Harvard, and then there is something that's happening at Stanford with the Amy group, who are trying to collate different data sets together. But I think more effort is needed over here, and maybe you also want something coming from higher up beyond even academia, maybe, like, for example, the government getting involved in terms of creating these resources for everyone to build and train on. But right now I would say there aren't enough resources, like open source medical data sets. And it's understandable to a degree, because there's so many challenges in creating these data sets, right? I mean, in terms of acquisition, consent, de-identification, and the legal implications, the privacy implications, and everything. And it's a lot of work. And a lot of the data set creators outside of academia maybe are not also currently incentivized to do that. And so they would rather maybe prefer to keep that closed and then license it so that they can, extract some more value out of it. So yeah, I think resources for creating medical data sets are, I think, not just resources, but generally medical data sets, I think we could do a lot more over here. It's lacking. And I think that has kind of like perhaps slowed down progress in medical AI as well. I mean, there are a lot of papers that are written, but they're all done on like very small data sets. And as soon as you take them from one environment in which they are trained to the real world, they break often in catastrophic ways. And so I think that comes down to the quality of data that people are able to get hold of to train these models.
Yeah, I do think that the availability of these open source high quality data sets is it's got to be one of the main themes or the main hurdles or the main challenges that implementing AI in medicine is going to have over the next sort of 5 to 10 years. Uh, Zooming in back, going back into a bit more detail onto the quality of the data sets. What do you think? We've not just got, say, the data and the quality of the data and the size of the data sets, but we've also got the ground truths within the data sets, which within medicine can be really subjective. So, what are some of the best efforts that you've seen to improve the quality of ground truths in medical data sets?
Yeah, I think that's a great question. Ultimately, when you have data sets in imaging, you want them to be associated with real world outcomes because they are more objective. Like, for example, if you have a data set of like cancer images, then you want to know the real world outcome. But that means that data set has to be collected over a period of like maybe a decade, if not longer. And so it becomes tricky. And so you have to perhaps like resort back to the subjective radiologist or the clinician's opinion and use that as your ground truth. I think always having a panel of clinicians vote and using, ground truth aggregated with a panel is better than having a clinician, like a single clinician, for example, giving you a score and using that to train these models. Having said that, again, that is extremely expensive and laborious to do, right? So again, it is one of those things where I don't necessarily think we can do much in terms of scaling that up further. But what we can do is like train AI models that require less amount of supervision, or they can use supervision in other forms. So I think that is where we are getting better at, where we are able to build AI systems that can learn using self-supervision or unsupervised data where there are no labels, and the models can build up like good representations and models of the world. And then these models then become remarkably more data efficient. And so when you need to teach them a new task, maybe they don't require like tens of thousands of examples, they just need 100 examples, and that makes this easier. So, and then the other part is as you build out more flexible multimodal models, for example, models that can understand language instructions, then maybe you don't have to explicitly do this laborious annotation task that you may have to do. For example, you may be able to like provide a natural language instruction about how, for example, a nodule or like something on a radiology image might look like. So it's similar to this analogy of, you don't have to show a child the image of a zebra for it to understand what a zebra looks like. You could say, oh, a zebra is a horse with black and white stripes, right? And then the child may never have seen an image of a zebra, but when you show it an image of a zebra, it may be able to understand that. And so we want to get our models to that state where maybe you don't have to explicitly show it an image of something or some data, but rather be able to like impart that knowledge through language, just as we do to other humans and kids in our school and everywhere else in university. And so I think that is the more promising route, where instead of trying to curate maybe more bigger and bigger data sets for training, it may be more interesting to see how we can train these models to learn more efficiently from data. But I think it's still important that we have very strong, high quality data sets for evaluation. And especially in these era of like large language models, where given these models tend to be trained on pretty much everything on the internet, so it may be very difficult to assess these models because we don't know if it's part of the training data or not. So it's important, for example, national bodies hold back, some data that is golden, that's clearly never seen by these models, so that we can properly assess the progress made and understand whether these models are actually like doing what they claim to do or not, right? And so I think that is really, really important as well. And then and maybe one quick thing I'll add is medicine is a very dynamic endeavor. It's based on science, and science keeps updating every week with new research, like tons of new research, right? And so the knowledge evolves, and so you also want these models to be able to like dynamically pull in new knowledge and be able to use that and reason that. And so your evaluation sets should also kind of like account for that.
Fantastic. And what data sets did you train MedPalm
on? So the MedPalm version itself built on the Palm model. The Palm model was trained on a lot of data from the internet. I wouldn't go too much into the details. For MedPalm, we used a bunch of medical domain specific data. Again, the details are in the paper with a bunch of expert demonstrations as to how to do medical question answering. And we use that to align the model to the medical domain.
Okay, fantastic. And are there any books that you found particularly useful?
Oh, I enjoy reading textbooks. So maybe I'm one of the few who says that, but like I feel like that's the best way to understand and go deep into a topic. A lot of the textbooks on my table right now are deep learning and AI textbooks on reinforcement learning, on probabilistic machine learning. But I'm also trying to understand how the brain and the human body works. So I have a principles of neuroscience textbook on my table right now. Another textbook on biomechanics and body movement, because I feel like we still don't understand ourselves really well, and the kind of AI that we are building does well on many tasks that humans do well, but the intelligence itself that we have so far is kind of different. But then there are also many other things that humans do remarkably well. For example, mathematics that AI today doesn't do well at all. And so if we want to improve AI further and make it like maybe more efficient, and not like burn literally forests while training and deploying these models, I think we need to go back to the principles of how the human brain evolved and how the human body evolved. And so I'm trying to understand that a little bit more better, to derive inspiration for more research. Beyond these topics, I do enjoy my fair share of autobiographies. The most recent one I read was this one of Jennifer Doudna, called The Code Breakers. I thought it was more of a thriller. I don't know, everyone had this idea that academia and science could be so thrilling, and there's like so much competition and everything around patterns and inventions and everything. But it was a fun read. It was kind of eye-opening as well, because I've not worked in academic settings. I've worked primarily in industry research settings, and so it was fun to read that and get a sense of how that would look like if I had ever chosen that career. Yeah, and then the other interesting book that I read recently was called More from Less. It is this idea that even though we as a civilization have been progressing, and like our population is increasing around the world and everything, but in terms of our actual material use of resources, that's actually going down, and we are able to do more from less use of resources. So this idea that we're actually consuming more and more as a civilization may not necessarily be true. It might be true in some aspects, but there are many other areas where if you look into the data, look deep below, you would see that we are, because of the technology progress that we are making, the amount of resources that we are consuming, even though our population has increased and people are getting used to a higher standard of living across the world, the actual use of resources is going down. And I think that is a very interesting idea. And in general, as you are working in large organizations, and in settings where there's a constraint on resources, both time and people and everything, being able to have principles of doing more from less people is, I think, a good idea. And not people only, but all, like in general, more from less resources is, I think, a good idea. And so I think that was a pretty interesting read for me.
Okay, great. And do you think you've got any approaches to your projects that you found particularly useful along the way?
Yeah, I think it's always useful to work on projects that are interdisciplinary in nature, because I feel like if you're only working on something that's in your field, you may, for example, be too in depth and be you may miss the forest for the trees, basically. And I'm a big believer in the fact that magic happens at the intersection of fields. And in particular, I'm very biased towards this intersection of AI and medicine and biology, simply because I think AI is the most profound technology of our lifetimes. And medicine is probably the one field where it can have the most impact in terms of reducing the burden of diseases worldwide, and then allowing people to live lives to their fullest potential. And And then the third aspect is more around biology and understanding, disease mechanisms. And maybe if you look at it more broadly, like, and if you're thinking about aspects around synthetic biology, understanding nature. And one fact is, like, we have this notion of Moore's law in computing, where our computers become faster every 18 months. It's not completely accurate, but that's one way to put it. But if you look at the progress in terms of like generating biological data, that's actually improving faster than even Moore's law. So if you look at some of the sequencing technologies that we have, that is getting even better and better, right? So I think we are very well on our way to biology being the the fastest data generating flywheel in the whole world. And that has, again, a lot of implications for AI, because now we have AI systems that can process all that data, make sense of the data for you, and give you novel insights. And that can be used to do all sorts of crazy things, right? And from understanding diseases to designing of new drugs, new materials, biomedical knowledge discovery, improving access to care for everyone, and so all sorts of implications. So I feel this intersection of AI, biology, and medicine is a magical place to be in the next decade or two. And I think we're going to see, yeah, profound changes. So yeah, my only tip is, like, think about working at like the intersections of such big fields.
Yeah. Yeah, fantastic. Completely agree. Absolutely, such an exciting time and exciting space to be working in. And do you have any advice? So, other than the intersectionality of spaces, do you have any other advice for students?
Um, yeah, don't be afraid to chase your curiosity, and because I feel like as we grow up, we kind of tend to lose that part of us, which is doing things just for the sake of trying to understand or get a better sense of something, or just because we're curious about something. Um, so yeah, I think on the one extreme, you should not be only doing things that you're curious about, because then you may not end up having a lot of impact. But then if you can, identify like a goal, um, right? Uh, and then if you're flexible in terms of how you get over there, so and then allow your curiosity to help you get towards that goal, then I think you can do a lot of magical new things. And so I think the key is this balance that many people miss out on. Like, a lot of people, particularly coming from academic settings, may be more interested in curiosity driven research, whereas people who work in industry, for example, may be more interested in outcomes driven research. But I think the key is this balance, where you want to have like an extremely ambitious goal, something that potentially changes the world if you get it right, but then
Mm.
be very flexible on the path that you take to get over there. And so let your intuition and curiosity guide you in terms of getting over there. So I think that is one. And then I would say, yeah, never be afraid of doing things, of thinking of yourself as an outsider, because I think with the internet and maybe even LLMs, I think the ability to do new things, learn new things, it's just getting easier and easier and easier. And I think there is no
Mm.
constraints, right? I think so. For me personally, I had no idea of medicine like 5 years back. I don't think I still know much about it, but I think I can probably positively contribute to the field. And so even if you're an outsider, don't think about it that way. I think you can still have a lot of impact. The key is to have passion for that problem, and the motivation
Mm.
to go and have a dent, and make a dent in there.
Brilliant advice. Love that. And this is so the last question. I'm now at the stage where I'm ending every single episode with this last question. What are your thoughts on AI safety outside of medicine?
Um, yeah, I think it's a great question, and honestly, for me, I maybe haven't formulated my thoughts on this really well. So there is obviously this doomsday scenario where AI, becomes so powerful in the next few years that it might end up uh, killing everyone or whatever. I don't subscribe to that. Um,
Mm.
but yeah, I mean, it is a known fact that these models are becoming powerful, and we know how, like, the potential implications of that in a domain like medicine, or in biology, where these models may be potentially used to do um, harmful things, like create a new virus or whatever. Um,
Mm.
But it's also true that technology almost always has been dual use. That was true for electricity. Um, that was true for vehicles and automobiles. That was true for everything else since then, right? If you wanted to use that nefariously, you could use it. But then I think the beauty of human civilization is the fact that we've always found a good way to constrain those parts of the society and prevent them from using it that way, and allowing the real potential of that technology to flourish. And I still have my hopes on humanity, and I think we will be able to find a good way to make use of AI and make use of it to realize all our potential.
A massive thanks to Vivek for taking his time. You can find the links to his work in the description. Thanks very much for listening, and catch you next time.